We'll start the topic of polynomials by looking at the binomial theorem. Imagine you were trying to expand x plus 3 all to the power of 5. Now, first of all, the answer is not x to the 5 plus 3 to the 5. So let's just forget that for the moment. What you could do is use year 10 techniques to do it. So you'd write x plus 3, x plus 3, x plus 3, x plus 3, and x plus 3. And what you would do is multiply those to get a quadratic, then by that to get a cubic, then by that to the quartic, then to get the power 5 like that. It would take a long time and you'll probably make some mistakes along the way. Now, there is an easier way. It's not ridiculously easy, but it's easier. Consider the expansions of the binomial powers shown below. So if we were expanding x plus b to the 0, then the answer is 1, because anything raised to the power of 0 is 1. I'm just going to write that there. If I've got x plus b to the power of 1, that's just x plus b. Noting that the coefficients there are 1 and 1. What about a perfect square? It's going to be x squared plus 2xb plus b squared. 1, 2, 1. Now, what I'm going to do is write this next line here without looking at the next one in the line, and I know what's going to happen. So that's going to be a 1, 3, 3, 1. Notice the coefficients there, 1, 3, 3, 1. That's when I expand a perfect cube, I get exactly those coefficients. And the way the coefficients are found is by adding the two numbers above them. Now this one here, the 1, has one number there, which is 1, and let's say that that one's a 0. So 0 plus 1 is equal to 1, and that's how we get the coefficients there. Right, so we can get the next row, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc., etc. Okay, so that's the coefficients for a power 5 expansion. They would be the coefficients when I expanded that out. And these coefficients actually fall out when we use an arrangement. This arrangement here called Pascal's Triangle, named after Blaise Pascal, a famous French mathematician. There's all sorts of patterns in Pascal's Triangle, but it just so happens that the coefficients of a expansion like this also fall out of Pascal's Triangle. There's Fibonacci in here somewhere. I can't exactly remember where, but you can find Fibonacci sequence in there, all sorts of other things. Now, you might remember this formula from about the end of term 2 last year, or the end of unit 1 last year, and we use this formula when we work out combinations. Now, combinations, recall, are written like this: 4 choose 2. Okay, and that's the number of ways 2 objects can be chosen from 4 objects. Alright, now using the formula we can see that it is going to be n factorial, which is 4 factorial, r factorial, which is 2 factorial, times n take r factorial, which is 4 take away 2, which is 2 factorial. Now that's 4 times 3 times 2 factorial over 2 factorial times 2 times 1, but we're not going to multiply by 1. That cancels with that. That cancels with that. It's equal to 6. Now, it's interesting to note that that also can be found. So the 4 choose 2 can be found in Pascal's Triangle. And here's where. So we're going to call this row the 0th row, the 1st, the 2nd, the 3rd, 4th, and 5th. Now 4 choose 2 is going to be in the 4th row, okay, given that we've got a 0th row here. And this item here is going to be 4 choose 0. This one will be 4 choose 1. 4 choose 2, that's the one that we just found out, is 6. 4 choose 3. 4 choose 4. So what Pascal's Triangle will do is help us evaluate some combinations. Many students used this Pascal's Triangle to help them evaluate a combinations question on the 3-4 exam 1 last year. So it was certainly interesting to note that. Okay, so here would be a power 6 expansion. So this is binomial notation. think that's what it's called. I'm going to call it that. That's just the same as 6 choose 0, 6 choose 1, 6 choose 2, etc., etc. So some things to note. The value of the exponents of each term sum or add to n. So what am I saying there? That's x to the 6, b to the 0. 6 plus 0 is equal to 6. That's b to the 1. 5 plus 1, 6. 4 plus 2, 6. 3 plus 3, 6. That's important to know that. Convention that the power of x decreases from left to right. To the 6, to the 5, to the 4, to the 3, to the 2, to the 1, to the 0. But if we're doing this expansion here, what will happen is the power of x increases from left to right. That is, it'll start at the smallest, then get bigger and bigger and bigger and bigger. So just watch the position of the x. Now the number of terms in the expansion will be n plus 1. Okay, so that's 6. It's going to be 1, 2, 3, 4, 5, 6, 7. 6 plus 1 is 7. Now to find a particular term, what we use is this formula here. And I've got to confess, I don't actually use that formula, but I believe it would work if we wanted to. Okay, and this is also more generally the case here. But again, rather than look at long and complicated formulas, let's just do it, and hopefully you can sort of see where this is going. Right, so we're going to do the perfect cube expansion 2x plus 3 to the 3. Right, so what we want to do is generate Pascal's triangle, or 4 rows of Pascal's triangle. So here's the first, second, zeroth, first, second, and third. The third row here, or row 3, if we've got a 0th row, will give us the powers, rather the coefficients for a power 3 expansion. Alright, so knowing that they're our coefficients, let's get started. So when I expand that, I'm going to get 1 as the coefficient. I'm going to get 2x to the power of 3, 3 to the power of 0. Next coefficient is 3, 2x to the 2, 3 to the 1. Now how did I know that? 3 plus 0 is equal to 3, 2 plus 1 is equal to 3, 3, 2x to the 1, 3 to the 2, 1 plus 2 is equal to 3, and finally 1, 2x to the 0, 3 to the 3. Alright, now let's evaluate this. So we've got 8x cubed, 3 to the 0 is 1, times 1, plus 3 times 4 is 12, 12 3s are 36. Hang on, did I get that right? 3 times 4 is 12, 12 3s are 36, yep. Okay, this one here is 9, 9 2s are 18, 18 times 3. x, and our last one is going to be 1 times 1 times 3 to the 3 is 27. Okay, so we can check this out on the calculator as well. So the function we want to use is transform expand, and you feed it the perfect cube or the thing you want to expand, and there it is there. Okay, it can also be used to find the coefficient of certain terms in an expansion. So this one here is going to have a power 7 term, power 6 term, power 5 term, power 4 term, and a power 3 term, and it's the power 3 term that we want to get the coefficient of. So what we're going to have to do is generate 8 rows of Pascal's triangle to help us. So we got 0, 1, 2, 4, 5, 6, 7. This is the one we want. Okay, so that's the row. Alright, so here's the coefficients. So this is going to be the power 7, power 6, power 5, power 4, power 3. So it's going to be 35. It's going to be 2x to the 3 because that gives us our power 3. And it's going to be 3. And 3 plus what will give us 7? This one's got to be 4. Right, so this is still not a really easy one to evaluate. Alright, so what we need to do is it's going to be 3 to the 4. Now 3 to the 4, 3 to the 3 is 27, 27 to the 3 is 81. So I've got 81 multiplied by, this is going to be 2 to the 3, which is 8. So we're going to get 648, and then I'm going to multiply 648 by 35. 24 to 32, I think. 6 5s are 30, yep. 8 3s are 24, 2, 4 3s are 12, 14, 1, 6 3s are 18, 19. Right, let's tally it up. Okay, so we're going to get 22680 x to the 3. So therefore, coefficient is 22680. We can try that by simply putting a power 7 here, scooting across until we find the cube term, and there it is there, 22680. Got it right. Okay, find the coefficient of the power 5 in the expansion. Okay, so this is a power 7, so we're going to be in the same row. Now you might think we go x to the 7, x to the 6, and x to the 5, and that's going to be our coefficient. But what we need to note is you do need to look at what you're actually expanding. So if we were to use this one here, it would be 2x to the 5, 1 on x to the 2. And what's going to happen is this will cancel out. So it's going to be x to the 5 when I raise both terms to the 5. It's going to be x to the 2, which will leave x to the 3. So that's incorrect. And so what it's going to be is this same one here. Now let me explain. No, it's not actually. I think it's going to be this one. Right, so yeah, it is going to be this one. So 7 is going to be our coefficient. We've got 2x to the 6, 1 on x to the 1. Right, now how did I know that? Because I know that this will be x to the 6, and this will be x to the 1. 1x will cancel out with this, leaving us with x to the 5. So this is going to be 7 multiplied by, now 2 to the 6, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64, x to the 6 over x. That'll cancel out, giving us the x to the 5 that we want. 64 times 7 is going to be 244. 448 x to the 5. Alright, let's do that. 1 on x. 448 x to the 5. So we were right. So we're going to say, or conclude rather, that our coefficient is 448. Alright, so note the exercise is on or in Appendix 3, page 765, so it's not in the polynomials chapter itself.